For v equal to 0, we set the function equal to 0. 0 equals 16 minus x squared plus y squared. I see an x squared plus y squared. So I'm going to make that on its own. I'm going to add x squared plus y squared to the left. So then x squared plus y squared equals 16 gives me a circle of radius 4. That's for v equals 0. And for v equals 12, 12 equals 16 minus x squared plus y squared. I add the x squared plus y squared over there. I subtract 12 over there. 16 minus 12 is 4. So I get x squared plus y squared equals 4, which is a circle of radius 2. So my contours or my level curves are these circles. This circle of radius 4, and we do need to label it as gosh, a little scratchy there, sorry. We do need to label it as the contour where v equals 0. And then here, the circle of radius 2, we need to label the contour v equals 12. So that's how we answer the first part. I was looking at just so you guys know, I got the inspiration for this from an old 17C midterm from Lewis, actually, back when they were using a different textbook. So his original problem was something more like this: 9 minus x squared plus, I think, y. It was like y over 2 squared, like that. This was his original function. And when you like did v equals 0, you got x squared plus y over 2 squared equal to 9, which doesn't give you a circle, it gives you an ellipse. I don't really think you'll see something like that, but just be aware. The way you would graph something like this is if you set y equal to 0, you get x equal to plus or minus 3. And if you set x equal to 0, you get y equal to plus or minus 6. So it's an ellipse like that, if that was your equation, just so you're aware. It's something he's asked before, so I thought maybe. So then part B says, plot the point xy equals -2, 2 on your graph. So there it is right there, -2, 2. It's definitely between the two circles. Right? The circle of radius 2, it's outside of that, and it's inside the circle of radius 4. And then, based on your contour plot, darn it, sorry. So I wrote that question slightly wrong. I apologize. No, I didn't. I'm kidding. I wrote it totally right. Never mind. I did not write it wrong. Good. Is the function f of xy increasing or decreasing in the y direction at this point? So if we start here and we go in the y direction, which is up, are we increasing or decreasing? Well, let's see. From over here, right, it looks like we're moving away from function values equal to 12 and closer to function values equal to 0. So it looks like our function values are decreasing. We're moving towards a lower level curve, not a higher level curve. So I would say the function values are decreasing. And if I wanted to justify that, the words I would write would be because we are moving towards a level curve with a lower value, or lesser value. On the other hand, if we started moving to, so just not to ask this question, but if we started moving to the right, we would say that the function was increasing because between this level curve and this level curve, we're moving towards the one that's a higher value. So the function values are getting larger. So that's kind of how you can tell. If you're moving towards bigger function values, with level curves with bigger numbers, you're getting bigger. If you're moving towards level curves with smaller numbers, you're getting smaller. Let's see. Let's look at part C. Actually, go ahead.
For the level curves in the y direction, couldn't you make the same argument as well if you move, say, like down, right, instead of going up?
So if someone says the y direction, they specifically mean the positive y direction. Same for x. If someone says the x direction, they mean the positive x direction. So there was a homework problem a while back where they asked about moving like in the I or j direction. The I direction is the x direction, which is to the right. The j direction is the y direction, which is up. And then the negative I direction is left, and the negative j direction is down. So if someone says the y direction, they really mean up, and if someone says the x direction, they really mean across. But you're probably right. They should probably be more specific. They should really say, I'm going to move in the positive j direction, or I'm going to move in the negative j direction, or the positive I direction, or the negative I direction. Let's see. So let's look at the next part. Find the partial derivatives. So I want to find del f del x, the partial with respect to x. So the derivative with respect to x is just going to be negative 2x. And then I actually want to find the partial at the point. Right, that's what the question is actually asking me to. So I'm going to plug in negative 2 for x and 2 for y into this. I'm just going to get negative 2 times negative 2, right? Because there's only a place to plug in x, and get 4. Let's find fy. Fy is going to be negative 2y. And then when I plug in the point negative 2, 2, I'm plugging in 2 for y, and I'm getting negative 4. Or I should say it's negative 2 times 2, which is negative 4. And then to answer that last part of that, how does this compare to your answer in part B? Well, it matches, right? When we're talking about moving in the y direction, we said the derivative should be negative, and the partial derivative in the y with respect to y is also showing that. The partial derivative with respect to y is also negative, so we're good to go there. Yeah. The last question, I just kind of tacked on at the end, asks, from the point negative 2, 2, in what direction would the function v have the greatest rate of change? So what's the direction of the greatest rate of change from the point negative 2, 2? Okay. Someone asks you about the greatest rate of change, the answer is always the gradient. Meaning, if they're asking for the direction, it's going to be the direction of the gradient. If they're asking for the magnitude, it will be the magnitude of the gradient. So we need to find the gradient at that point. So the gradient of this function, well, partial, in fact, we already have all the pieces, right? It's this partial in the x component, this partial in the y component. So it's negative 2x, negative 2y. And then we're going to plug in the point negative 2, 2. So if we then say the gradient at negative 2, 2, we're just going to get, in fact, we probably could have just used what we did, right? We're like, oh yeah, it's just this and this. So it's going to be 4, negative 4. So we have to be careful though, because even though this vector is the right direction, right? It's pointing, you know, the vector is pointing over and down. Let me just draw the picture up here, right? So from here, right, the vector is actually pointing back towards the middle, which again makes sense, right? Because the gradient should cross your level curves perpendicularly and try to get bigger. So 4, negative 4 would be right over 1, 2, 3, 4, down, right? It would give me like, this would actually be the vector 4, negative 4. Starting here and ending here. And the thing is, when you want a direction vector, you want a unit vector. So you have to take your direction vector, 4, negative 4, and divide it by its own magnitude. The magnitude of this vector is the square root of 4 squared plus negative 4 squared, which is the square root of 32. Which you could simplify, but we don't really care that much. So then my answer would be 1 over the square root of 32 times the vector 4, negative 4. That would be the direction that this function increases the most rapidly from the point. And that makes sense, because if you think about it, right, if we start here, if you want to get the biggest, fastest, you should move straight towards your bigger level curves, which is what we're doing. Questions about this problem 1 before we move on to problem 2? Also, I do have office hours right after class, so if you have questions about things you don't ask them that, you can always ask them in office hours right after. Let's take a look at problem 2. So problem 2, I think is pretty straightforward. Oh, can you go show that? Yeah, of course, yeah. I will also mention while I'm here, if someone asked you to draw the direction that you would go in to have the greatest the greatest rate of change for your function, the direction you should go in should be the direction that is crossing your contour lines or your level curves perpendicularly, right? So if you take a look at this, right, the angle that this is crossing this at is exactly perpendicular. So if I said I was starting like, or let's say I was starting at the point -3, -1, the direction that I'm going to cross, and for circles, it's always just pointing towards the center, right? If I was going to cross this perpendicular, I would be moving exactly in that direction. So someone had to draw, like, oh yeah, I want to make that angle there a right angle. That's going to be the direction that the function increases the most rapidly, which would be the gradient. Okay, so let's find the linearization of f of xy equal to x squared y plus 2x e to the y at the point 2, 0. So we have to find the partials and then throw them all in that big formula. So actually, before we find the partials, we really should find the f of 2, 0. So f of 2, 0 is going to be 4 times 0 plus 4 times e to the 0, which is 4. Right, 0 plus 4 times 1 is 4. And then our fx is going to be, so the partial with respect to x is going to be 2xy plus 2e to the y. And then plugging in 2, 0, fx at 2, 0 is going to be 2 times 2 times 0 plus 2 times e to the 0. That's going to be 0 plus 2. And then fy, partial with y is going to be x squared plus 2x times e to the y, right? The derivative of x squared times y is x squared times 1. The derivative of 2x times e to the y with respect to y is the 2x hangs out, and the derivative of e to the y is e to the y. And then we're going to plug in 2, 0, so fy at 2, 0 is, let's see, 2 squared is 4 plus 4 times e to the 0. 4 plus 4 is 8. Right, so now we throw everything into the big formula. The big formula being that your linearization, or your, so you can either use L of xy if it's a linearization, or you can use Z if it's a tangent plane. It really is going to be f of x naught y naught plus the partial with respect to x at 2, 0 times x minus x naught plus the partial with respect to y at 2, 0 times y minus y naught, where this is your x naught y naught. So that's going to be L of xy equal to f of 2, 0, which is 4, plus fx of 2, 0, which is 2, times x minus x naught, plus fy at 2, 0, which is 8, times y minus y naught. Important thing to take note of here. You can simplify this. You should not simplify this. It is really not in your benefit to simplify this as 4 plus 2x minus 2x minus 4 plus 8y minus 0. But that's actually not going to help you do the second part of this question. So you really, really, really should, if you find linearization, leave it like this. I mean, maybe simplify this to just 8y, but essentially leave it like this. Because the point is that now when we plug in, so the second part B is use the above linearization to approximate f of 2.1 comma 0, negative 0.1. F of 2.1 comma negative 0.1. That's going to be approximately equal to the linearization at 2.1 comma negative 0.1. And the point is that this point is close to that point, so that these differences should be relatively small. So we're going to get 4 plus 2 times 2.1 minus 2 plus 8 times negative 0.1 minus 0. So that's going to be 4 plus 2 times 0.1 is 0.2. And then 8 times negative 0.1 is negative 0.8. So that's 4.2 minus 0.8. That's going to be 3.4. And then if you look at the problem, they tell us that the actual value was 3.359. So yeah, we're pretty good with that, right? That our answer is close, which it should be. But definitely, it pays to leave it like this and not to do anything more with it. Questions? Erase the other side. So I feel like this test isn't like, I feel like this practice test I've given you guys is not totally unreasonable. I feel like he could ask something with this many questions and it would probably be, it would be hard for sure, but it would be not out of bounds. So you should prepare for something possibly as long as this. So let's look at this last one here. Find all critical points of this function. I mean, so really question 3, right? I broke it down into 3 parts, but really I could have just written the question as find and classify all the critical points of this function, and it would just be not be broken up into 3 parts. So it really is one question. I've just written it in smaller parts so it's easier to digest, which is definitely how you should think of it, right? If someone says find and classify the critical points, we're like, okay, first find the critical points, then calculate D, then plug those things into the D. Okay, so let's see. Our function here is 3x squared y minus 6x squared minus y squared minus 8y. And hopefully I didn't jack this one up. I was making it up earlier today and it took a little while to get it so the numbers came out nice. I'm assuming I didn't make any mistakes. So we want to take the gradient and set it equal to 0. So the gradient is the partial with respect to x, which is 6xy minus 12x minus 0 minus 0. Then the partial with respect to y is 3x squared minus 0 minus 2y minus 8. Okay, and this is where things get a little bit dicey. You have to kind of decide which equation you want to work with first. You can work with this one, but the problem with this one, so you could, so actually I wouldn't work with this one first. Let me just tell you why. If we set this one equal to 0, 3x squared minus 2y minus 8 equals 0. You can solve this for y. 3x squared minus 8 equals 2y, and then y equals 3/2 x squared minus 4. The problem with that is then you have to plug that in here, and then you're going to get some cubic thing. So typically, if I have a choice between the 2 parts of the gradient that I'm setting equal to 0, I try to look for the one where I can either factor something out or where the powers are lower. And actually, that's kind of both of those things are true here. If you take that first equation, 6xy minus 12x, set it equal to 0, what can I factor out? It's okay, Zach.
6x.
Right, we got to practice. So 6x times y minus 2 equals 0. And then you get 2 possible, well, I would say this equation, you have 2 possible solutions. Either x equals 0 or y equals 2. So if you set x equal to 0, this one will be 0. If you set y equal to 2, this will be 0, right? Because if x is 0, you get 0 minus 0. If y is 2, you get 12x minus 12x. So either one of those make this 0. But either one of those don't actually make this 0. If you set x equal to 0 here and y equal to 2, you get 0 minus 4 minus 8, which is negative, right? So that's the thing. Once you find solutions to this equation, then you have to plug those in to the other one. So if we plug in, and I guess since we did this work, we might as well. I still think, so typically I wouldn't have done this really. So if we plug in x equal to 0, we're going to get negative 2y minus 8 equals 0, negative 2y equals 8, y equals negative 4. So one of our points is 0, negative 4. I feel like, no, I guess that's all right. So I feel like I might have made a mistake. I don't know. I always feel like I made a mistake until I get the answer I was looking for. So then the other one we're going to plug in is y equals 2. Oh, no, this is right. Yeah. So we plug in y equals 2 into this equation. We're going to get 3x squared minus 2 times 2 is minus 4 minus 8 equals 0. So that's 3x squared minus 12 equals 0. You can factor or you can add the 12 to the other side. So 3x squared equals 12, x squared equals 4, x equals plus or minus 2. So the critical points I get here are both when x is positive 2 and y is 2, and when x is negative 2 and y is 2. So those are my 3 critical points: 0, negative 4, 2, 2, and negative 2, 2. Okay, let's calculate D. Okay, fine. Write this on the other side. So if I was calculating D, I would use this, right? I'd be like, oh yeah, there's my gradient, which is fx fy was 6xy minus 12x, and 3x squared minus 2y minus 8. Right, because you've already got your first partials there. Don't do more work than you have to. Don't repeat the right. You've already found the first derivatives, don't find them again. So then to find fxx, we're going to take the derivative of this with respect to x, which is going to be 6y minus 12. To find fyy, take the partial of this with respect to y. Derivative of that is 0. Derivative of negative 2y is negative 2. And the derivative of negative 8 is also 0. And then finally, the mixed partial should be the same either way. Here's fx. If you take the derivative of this with respect to y, you're going to get 6x minus 0. Fyx, if you take the derivative of fy with respect to x, you're going to get 6x minus 0. So good, 6x. So then D would equal this times this minus this squared. So I would probably write it as negative 2 times 6y minus 12 minus 6x quantity squared. You might even factor out a 6 from this. I don't know. I probably wouldn't, but you can say if I factor out a 6, it's negative 12 times y minus 2 minus 6x squared. And now we have to plug in our 3 critical points. What were they? 0, 4, so negative 4. Okay, so we got 0, negative 4. We've got 2, 2, and we've got negative 2, 2. Each of those have to get plugged into D, and then we have to determine if it's a min, max, or a saddle. So let's do 2, 2 first. Let's do the bottom first. So I plug in negative 2, 2. So let's say I'm going to get negative 12 times y is 2. That's going to be 0. Minus 6 times negative 2 is negative 12 squared. And 0 minus, so be careful here, right? A negative number squared is positive, right? Whatever is over here, if it's squared, it's going to be positive, or unless it's 0, right? It's 0. But you've got minus some positive numbers. This is going to be 0 minus 144, which is negative. And if your D is negative, what do we have? What do we have? We have a saddle at negative 2, 2. All right, and we're going to see the same thing happens at 2, 2. We look at 2, 2, we're going to get the same result. This part's still going to be 0. And as long as this part isn't 0, the whole thing's going to be negative. And you're going to get 0 minus 6 times 2 is 12 squared. So you're again going to get 0 minus 144, which is negative. So you have a saddle at 2, 2 and at, sorry, a saddle at negative 2, 2 and at 2, 2. So let's look at the last one, 0, negative 4. If I get negative 4 for y, we're not going to get 0. We're going to get negative 12 times negative 4 minus 2 is negative 6. Minus, if we plug in 0 for x, we're going to get 0 squared there. And the negative times a negative is a positive. So you don't actually have to see what, you don't have to know that 6 times 12 is 72. You just have to know that this is positive, minus 0, it's still positive. So if it's positive, that means we either have a max or a min. So when you see that D is positive, you say to yourself, I have to do more work. The more work you have to use, you have to check one of the second derivatives. Well, look, fyy is negative 2, meaning that second derivative is negative. It's concave down, so we have to have a max. So we have a max at 0, negative 4, because the second derivative, fyy, is negative. Or you could have checked fxx, right? If you check fxx, if you plug in negative 4, you would also get a negative, and you get negative 12. So either one you check, it doesn't matter which one you check, they'll tell you the same information.